Hello everybody, my name is Zhang from Jinan University. I'm glad to share one part of my research as a migration occurrence of palm olein during the interesterification catalyzed by Sn-1 specific lipase. There are 4 parts in the presentation: why we do this project, how we process, what we got, and what we will do next. Physiochemical properties of the particular triacylglycerol are dependent on the fatty acid chain length, degree of saturation, and the fatty acid position on the glycerol backbone. To enhance the technical properties of the natural oils, a process known as interesterfication can be performed to modify the triacylglycerol properties. Following interesterification, the alteration in the triacylglycerol molecular structure modifies the melting point, crystallization behavior, solid fat content, thermal properties, and the oxidative stability of the fat products. There are 2 common pathways to perform the interesterification: chemical interesterification and the enzymatic interesterification. Chemical interesterification is commonly practiced in the industry, and this process randomly rearranges the fatty acid positions. While enzymatic method has several advantages over the traditional chemical interesterification, such as it's a more flexible process that can be performed without the need of chemicals and its high efficiency. Besides, the enzymatic interesterification is a more specific process, especially when the process is catalyzed using a specific lipase. Hence, fats with desired physical and nutritional properties can be customized through the enzymatic method. They prefer used lipase in Sn-1 specific enzyme. The preferred used lipase is Sn-1 specific enzyme. The ability of Sn-1 specific lipase to affect the ester bond of the Sn2 position is weak, while the Sn-1 position as a bond on the glycerol backbone has the property of selective interesterification. Its industrial application has attracted much attention in food industry. Therefore, Sn-1 specific lipase can be used to prepare cocoa butter replacer with high requirements for the symmetry structure of the triacylglycerols, such as the SOS and the human milk substitute fat, such as the OPO. In reactions that involved the use of specific lipase, randomization process that occurred in Sn2 position is also analyzed. Present studies show that even though the enzymatic interesterification is a specific reaction, acyl-migration can occur alongside with the process, causing the randomization in the Sn2 position. Under the extreme interesterification conditions, acyl-migration is promoted and complete or partially randomized products can be obtained. Therefore, methods to evaluate the interesterification degree and the acyl-migration degree are beneficial as a means to keep the reaction under control and produce interesterified products which are Sn-1 specific. Many factors could influence the thesis efficiency and acyl-migration, such as reaction temperature, reaction time, reaction system, lipase, or even the support of the immobilized lipase. In this project, palm olein, which is rich in carbon 16 and carbon 18 fatty acid, as you know, most of saturated fatty acids are located in Sn-1 and Sn-3 positions, and the commercial Sn-1,3 specific lipase TL IM were used to study the acyl-migration roles during the enzymatic interesterification. Whether it is random interesterification or acyl-migration, the composition and the content of Sn2 fatty acid can be significantly changed, so the change roles can be monitored according to the change of Sn2 fatty acid under different reaction conditions. The common method of determining a fatty acid positional distribution as the Sn2 and the Sn-1,3 position is conducted by first hydrolyzing the ester bond at the Sn-1,3 position of triacylglycerols using the pancreatic lipase, and the products obtained from the lipolysis was then isolated using TLC. The Sn2 monoacylglycerol band was then scarfed off, and its lipase was extracted into diethyl ether and subsequently used for the fatty acid analysis by the GC. In an idle Sn-1,3 specific interesterification, the fatty acid composition in the Sn2 position remains unaltered. However, modification in the Sn2 fatty acid is often observed during enzymatic interesterification process in practice under certain conditions. A completely randomized fatty acid distribution is obtained. For example, one of the main triacylglycerol in palm olein is POO. During the Sn-1,3 specific interesterification, the triacylglycerol in the forms of POP and OOO will be obtained. From the figure, two new triacylglycerols are produced through the modification because of the acyl-migration. As the fatty acid composition of natural oil is more complex, we found that only by monitoring the change of a certain fatty acid is not good, and the degree calculated by different fatty acids is not consistent. In order to establish a more accurate method for analyzing and calculating the acyl-migration degree, the fatty acid composition of the reaction substrate was simplified into two categories: S, saturated fatty acid, and U, unsaturated fatty acid. When the system is random interesterification, the molar percentage of U and S in the Sn2 side will change to the molar percentage of U and S in the total fatty acid of the substrate, and the molar percentage of U and S in the total fatty acid of the reaction substrate can be seen as the balance point as shown in the figure. The calculation method of the Sn2 fatty acid change degree is as shown in the equation, where the U2 and S2 are the percentage of initial U and S as the Sn2 of the initial substrate. U2T and S2T are the percentage of U and S as the Sn2 after the reaction for a certain time, and U0 and S0 are the percentage of U and S in the total fatty acid of the initial substrate. dt is the distance from the point Sn2 to the point Sn0 after the reaction for a certain time t. and D0 is the distance from point Sn2 to point Sn0 at the beginning of the reaction. When dt is equal to D0, it shows that the Sn-1 3-specific lipase has the strongest catalytic efficiency, and there was no acyl-migration, and the interesterification only occurred at Sn-1 and Sn-3 position. While dt is equal to 0, the catalytic efficiency of the Sn-1 3-specific lipase was the weakest, and the acyl-migration was the strongest, and the reaction basically reached to the completely random interesterification at Sn-1 and Sn2 and Sn3 positions. Therefore, taking the percentage of U and S in the initial balance total fatty acid as the balance point, combined with the Sn2 side, Sn2 position U and S molar percentage change of the interesterification sample in the actual reaction process, the change degree of Sn2 fatty acid was quantified. Here are some results. The mechanism of acyl-migration was triggered by the nucleophilic attraction of free hydroxyl oxygen lone pair electrons of the carbonyl esters in glycerate anions, which would convert an unstable cyclic oral esters intermediate. We also found that the ring was initiated by the breaking of the carbon-oxygen bond of the original ester, which resulted in the migration of the ethyl group. The same two fatty acid composition of interesterification products with different reaction time were shown at the table. The closer the same two fatty acid composition after interesterification was to the overall fatty acid composition, the greater of the interesterification degree. Table shows that the same two saturated fatty acid increased significantly, indicating that with the increase of enzyme loading amount and the extension of reaction time, the acyl-migration degree of Sn2 was greater. The change degree of Sn2 fatty acid was calculated according to the equation. When the TLM was loaded 7%, the change degree of Sn2 fatty acid was increased to 62%. And when the reaction time was more than 8 hours, the acyl-migration degree reached around 100%. The enzyme addition and extension of reaction time promoted the occurrence of acyl-migration and significantly affected the catalytic efficiency of the Sn-1 3-specific lipase. And the acylglycerol composition were also analyzed. As the interesterification proceeded, the content of SSS type triacylglycerol and the UUU type triacylglycerol increased. The content of SUS type triacylglycerol decreased. A small increase in the temperature. The acyl-migration was found to be related to targeted yield and affected to the solid fat content profiles and other physicochemical properties. The crystallization rate after interesterification was improved significantly. From the DSC, after the interesterification, the melting and crystallization temperature increased, as well as the crystal microstructures were also changed after the reaction. Finally, by studying the enzymatic interesterification mechanism that is catalyzed by Sn-1 specific lipase, models for determining the acyl-migration can be established. Most reported that the acyl-migration was a side reaction of interesterification and should be inhibited. However, in some cases, acyl-migration could be positively applied if the desirable fatty acid at the Sn-1 position needs to be shifted to the Sn-2 position. So found that the distribution of fatty acid at the Sn-2 position was significantly affected by the acyl-migration, and controlling acyl-migration could improve the similarity of the cyclic products compared with the breast milk. This model is useful for the development of key technologies in producing structured lipase for food specialty fats processing conditions. Enzymatic interesterification performed in the traditional stirring tank reactor requires lower enzyme addition, but the longer reaction time leads to the occurrence of acyl-migration. This acyl-migration can be controlled by adjusting the reaction conditions to promote acyl-migration at the Sn-2 position to prepare the structure lipase which are rich in saturated fatty acid at the Sn-2 position. With the use of packed bed reactor, the reaction can be controlled by employing various types of specific lipase. In a packed bed reactor, the amount of oil in the enzyme reaction column is always in excess. The contracted reaction time between the oil and the lipase can be reduced by increasing the flow rate. For example, by using Sn-1 specific lipase, the interesterification degree can be controlled and the acyl-migration degree can be reduced. This will result in a more uniform distribution of fatty acid in the Sn-1 and the Sn-3 position, leading to the preparation of a symmetrical triacylglycerol lipase structure. Okay, this ends my presentation. Thanks for listening. Thank you very much.